Hello everyone, and welcome to this tutorial where I give you guys some insights to a hack that I found out recently on how to solve the Colebrook equation for determination of the Darcy-Weisbach friction factor, also referred to as the value of F, as you can see in this equation described here. The friction factor is extremely important as it's a dimensionless quantity that helps us determine the effect of friction on flow fluids, especially during the flow through a conduit or pipe in the turbulent regime. So the Colebrook equation is mostly applicable to the turbulent regime, that is friction, that is the Reynolds number that's greater than 4000. So I've used this multiple times in applications such as for sizing pumps and in line sizing of refrigerants. And for that you'll need some basic inputs which I have described here under the inputs, pipe friction losses. So we have a flow rate of water, and the flow rate is at 5 ounces a second. I've just converted that to the cubic meter per second value. I also know the diameter of the pipe that is carrying this water at this flow rate. That's 12.7 millimeters. I know the pipe's length. It's about 30 meters. I know the acceleration due to gravity, the temperature of the water, and the material of the pipe. Here I've just embedded a set of different kinds of pipes that have different values of relative roughness. So here for now I've selected the stainless steel option for our convenience. To the outputs tab, we have a set of values that are extremely important in determining the value of F. First is density, which is a function of the temperature of water here at 2 degrees Celsius. Then comes the dynamic viscosity, which again is the same. So these values can be derived from tables that describe the characteristics of water at different temperatures. I define the cross-sectional area from the available diameter. I can also describe the flow velocity of the water using the continuity equation, Q is equal to area times velocity. The absolute roughness of the tube that is carrying this fluid, in this case that's stainless steel, and its value is about 0.015 millimeter. The relative roughness, which is a value that considers the absolute roughness and the hydraulic diameter, which is 12.7. That's called relative roughness, and it is useful to us while we calculate the Colebrook equation. Then we have Reynolds number, which is a rho Vd by mu, rho being the density of the fluid, V being the velocity of the fluid, D is the hydraulic diameter through which the fluid is flowing, and mu is the dynamic viscosity, which is a function of the temperature of the fluid as discussed earlier. So determining Reynolds number from the relationship that I just mentioned helps you determine whether the flow is turbulent. Basically, if the value is greater than 4000, it is deemed as a turbulent flow regime. So considering that, we move forward into solving the Colebrook equation, which is specifically for turbulent flows and in rough pipes. As you can see, the Colebrook equation that I've described here has the value of F defined on either side, that is on the LHS and the RHS. So the regular run-of-the-mill method of solving equations will not work out here. We'll need to use an iterative method to get the best results. So I'm going to lead you step by step into how to do it in a very easy way, and I can even share the Excel sheets with you guys. So here we'll focus mostly on the RHS, the right hand side of the equation, and I notice there is a 1 by square root of F value. So on the RHS we see there is a value of 1 by square root of F, which we can assume to be 1 in our first trial, and you'll find out the method or the reason why we do that. So the 1 by square root of F value we assume to be 1. What I do in this cell here is evaluate this entire RHS value considering 1 by square root of F is 1. So when I evaluate that, as I double click on the cell, you'll notice that minus 2 log to the base 10 G9. G9 is the relative roughness by DH, E by DH, so I've considered both together. Divided by 3.7 plus 2.51 divided by Reynolds number multiplied by 1 by square root of f, and here the 1 by square root of f is referencing the upper cell, and that's 1. You will notice another important thing here is I've added the dollar signs to the other variables. That ensures that when I drag this cell down, those variables don't change their position, whereas this value changes its position. I'll get into that in more depth. So this value that I've got now is re-entered into this RHS. So now I go into my first iteration where I put my 1 by square root of f value not as 1 but as 6.4398. And then I resolve this equation. And when I resolve the equation, I get a new value. So all I need to do in Excel is just pull this cell down. So what happens is all the cells that have the dollar sign are referenced as is, but the kx value, which is 1 by square root of f, which I considered as 1, and I got a value of RHS here, that gets substituted into here. So each time, now I've got the 5.3373 value. Now I embed this value back into this equation. I solve the RHS, beg your pardon. And when I do that, I get a new value as this. Now I enter the same value here as the 1 by square root of f value, and then I get a new value, this. And I just drag this until about 20 times. And you'll start to notice that the values start to converge. The magnitude of those values look similar. That means you've reached the point where you're able to take a certain value as reference. So here now 5.4804 is our value of reference. Now what I'll do with this value is I'll just equate it to 1 by square root of f. So 1 divided by the square root of f is now going to be equal to this value. So if I consider this as an equation, and if I need to calculate the value of f, what do? I just bring this value back down or multiply this value on either sides of the equation. So what happens is I have 1 divided by this value whole squared, and that is my value of f, and hence we've obtained our Colebrook equation. And you'll notice that's the equation that's been embedded here as well.